The fundamental observation that underpins the field of psychiatric genetics is that we observe an increased rate of disorders, illustrated in blue here, in the relatives of those already affected with the disorder, compared to the general population, illustrated here in grey. Now, usually we describe the genetic contribution to psychiatric disorders through the term heritability, which is the proportion of variation in liability attributable to genetic factors. Now, heritability is estimated from observations of lifetime risk, but the link between these two isn't terribly intuitive. Now, the link comes from the theory of the liability threshold model, which was formalized by Douglas Faulkner over 50 years ago. In this model, we assume that the risk of disease, liability to disease, is underpinned by many, many genetic factors and many, many non-genetic factors, and together those factors add up to make a normal distribution of liability. And those who carry a high burden of liability above this threshold, in this case, I'm looking at a disease of 1% of the population, so 1% of this distribution is coloured blue, this proportion have disease. We can then think about the first degree relatives of these people and think about their liability distribution. Again, because even in them, the liability is underpinned by many, many factors, they will also have a normal distribution of liability. But if there's a genetic contribution, that the fact that we've ascertained on their first degree relatives means that their distribution is likely pushed up so that a higher proportion cross the threshold. So from two observable pieces of information, the lifetime risk in the population and the lifetime risk in relatives of those affected, the liability threshold model says what proportion of the variation in liability must be attributable to genetic factors to be consistent with these two observations and consistent with the fact that we know how genetic variants are passed from parent to offspring. Now, while we usually talk about the liability threshold model thinking about those normal distributions, another way that we can look at this model is by thinking about genetic liability on the x-axis rather than phenotypic liability, or we can think of this as being true polygenic risk score, compared to the y-axis of probability of disease in an individual. And then we get these S-shaped probability curves. So here we can imagine that someone could have a low genetic liability, a low probability of disease relative to their genetic liability. Still, they could get the disease because they have non-genetic factors contributing to their disease risk. Here we're comparing diseases which are uncommon in the population, 1%, versus common, 25%, diseases which have low heritability versus high heritability. With high heritability, we see that this S shape is much steeper than with low heritability, and when the disease is uncommon, the S shape starts to rise when the genetic liability is higher. So this S shape is actually fundamental to reconciling polygenic disease with the frequency of disease that we observe. And in fact, there's many, many models which can fit this S shape, but they're exchangeable. And the reason that we like the liability threshold model, or it's the one that tends to be used, is because it's so simple. You just need two parameters to generate different shapes of these S curves. It's important, of course, to remember it is a model, but so far observations from family studies and from genome-wide association studies suggest it is a useful model. So recently we published a review article which goes over some of these basic concepts. It has a technical supplement, and Bart Baselmans has made this very nice shiny app which helps visualize some of these concepts.
So we built an app which we call Judge, and Judge stands for calculating the heritability and relative risk and genetic correlation. And the first page basically shows the liability threshold model, also visualized over here. And you can play around with these sliders. So the first slider is to set the lifetime risk of disease. And the second slider, basically, you can set the lifetime risk of disease of those having one affected relative. So if you play around with these sliders, you can see that both the table as well as those two figures are automatically updated. And with the information provided in this table, you should be able to estimate the heritability. And if you have done so, you can click on this button and you can check your calculations. And if you want to have some more information about the liability threshold model or how you can calculate the heritability, you can click on the green question mark. So here's a little bit more background, for instance, how you can calculate the threshold based on the lifetime prevalence, but also it tells you how to calculate the heritability. So in the second screen of this tool, you can set the lifetime risk and the heritability of two different disorders. And with this information, you can estimate the increased risk in relatives. So the figure over here visualizes three different scenarios. So the top part shows you the results of the general population with the lifetime risk over here. And the middle part shows you the results of those having one affected relative. So here you can see the increased lifetime risk as well as the increased risk in relatives. And then the last part, the bottom part of this figure, shows you a more extreme scenario and shows you the results of the population having both parents affected. So with the information shown in this table, you can estimate yourself the threshold of those having one affected relatives. And if you have done so, you can check your results by clicking on this button. And if you want to have more information about the liability threshold model, as well as the risk in relatives and the heritability of liability, you can click on the green question mark and more information is shown to you. In the third screen of this tool, you can set the heritability as well as the lifetime risk of two diseases, and you can model the genetic correlation over here. And in this specific example, we have set genetic parameters mimicking schizophrenia as well as depression. And given the genetic correlation of 0.3, it is interesting to see that the liability of schizophrenia given relative diagnosis with depression shows hardly any increase in the lifetime risk. However, the liability of depression given relative diagnosis with schizophrenia shows a far steeper increase. The second thing that you can do over here is, besides modeling the genetic correlation, you can estimate the coheritability. And the coheritability basically is the proportion of the observed phenotypic correlation, which is explained by the genetic effects. You can calculate this parameter using the heritability of both phenotypes as well as genetic correlation. So to check your answer, you can click on this button. And if you want to have more information about the liability threshold model or the coheritability as well as genetic correlation, you can click on the green question mark.